Mr. K. Balraj is working as a polymer consultant and teaching fellow in the area of polymer science and engineering at CEG Anna University, Chennai. He has completed AMIE in electrical engineering at the Institution of Engineers India, Calcutta, and MTech Polymer Science and Engineering at CEG Anna University. He is also pursuing his doctoral research work in polymer technology. His area of specialization includes polymer rheology, polymer processing, characterization and testing of polymers, polymer blends and composites, and insulation technology. He has in-depth experience on plastic properties, testing methods, and the relevant standards. He has more than 15 years of teaching experience in polymer science and engineering, including instrumentation in polymer industries, engineering plastics, conducting polymers, and rubber technology at CEG Anna University. He has guided more than 30 MTech students in their research projects. He has presented more than 20 research papers in the national and international conferences in the area of polymer science. He has published 10 research papers in the peer-reviewed journals.
Welcome to UGC lecture series in polymer science. In polymer science, the course is polymer processing and mold design. This is the 7th part. In today's episode, we can learn about the feed system. What is meant by feed system? It consists of sprue, runner, and gates. In the last class, we have discussed about the runner layout, runner dimensions, and different types of runners. In continuation with that, in today's class, we will discuss about hot runner system and the different types of hot runner system, followed by gates. That will complete the feed system. In the hot runner system, there are two main types of hot runner system. One is called insulated runner. As the name itself implies, the runners are insulated from the mold. And the other one is the heated runners, where the runners are heated without insulation. The insulated runner, there is no separate insulation is not by any mechanical means, rather the plastic melt itself will act as an insulating layer. How it is, we will see shortly. Within the heated runners, there are two categories, the externally heated and the internally heated. First, the insulated runners. Insulated runner molds have oversized passages formed in the mold plate. That is, the passage the dimensions of the passage is comparatively higher than the normal runner molds. The passages are of sufficient size that under conditions of operation, that is when the melt is passed through that, the insulated effect of the plastic which is normally this will form a frozen layer on the runner wall, combined with the heat applied with each shot maintains an open molten flow path. You could see for this is a typical insulated runner system. There is no separate insulating layer provided, rather, so this is the melt passage, and then on the surface of this runner wall, you could see the frozen layer of the melt. The plastic melt gets frozen or it gets solidified, and it forms a layer over this runner, and this is going to act as the insulating layer. And this is a typical gate, and that is how the melt fills the cavity. Next, we will move on to heated runners. In the heated runners, there are two types. One is internally heated, and this is characterized by again an annulus flow passage with the heat being furnished by a probe and torpedo, which is in fact actually located in the passage itself. The heating element is provided in the passage itself. Now, this system takes advantage of the insulating effect of the plastic melt to reduce heat transfer loss to the rest of the mold. So, here again the plastic melt itself again acts as a barrier in heat transfer from the melt to the mold. In the externally heated, it consists of cartridge heated manifold with interior flow passages. We will see how it is. The manifold is designed with various insulating features to separate it from the rest of the mold, thereby reducing the heat transfer. So, here special care has to be taken, should be taken to provide these insulating features. So, otherwise there will be a heat transfer, there will be a loss due to the heat transfer from the resin to the mold. So, this is a diagram showing these both the internally heated and the externally heated. First, the internally heated, you could see the heater, cartridge heater is provided in the flow path itself. This is the passage for the melt, this is the runner, and the melt flows through this runner. In the passage itself, the heater element is provided. That's why it's called internally heated. Whereas in the externally heated, you could see the heater is provided externally. It's not going to be located inside the runner. Rather, the heater will just surround this runner, and then now there should be insulating features that will insulate the heat transfer from this melt to the rest of the mold. So, this is again cross sections of the flow channel in the actual manifold. First, the internally heated, the name itself implies. So, this the red colored cylindrical element is the heating element. This you could find is actually present inside the runner, and then this is the polymeric melt through to which this heating element is going to give the necessary heat. And now this polymer melt itself will act as insulating layer, so thereby reducing any heat transfer from this heating element to the rest of this manifold. So, therefore, one need not worry about the necessary insulation that has to be otherwise provided from preventing the heat transfer from this heating element to the mold. Rather, whatever the heat that is produced by this heating element, that should be entirely supplied to this polymer to melt it and then to flow at appropriate properties. And then in the externally heated, you could see the polymer is surrounded by a manifold block, and then these heating elements are provided on the surfaces. So, thereby here also again this polymer melt will again act as a insulating layer in preventing the heat transfer from the resin to the block. Now, if you look into the advantages of internally heated system, this prevents any leaking problems which would otherwise take place, and then it also provides a good isolation. As you can see earlier, this acts as a barrier from the heater to the mold, and also it provides good tip control. As the cartridge heater is provided on the passage itself, the exit from the runner to the gate is so smooth. As heaters are internal, there is no need for a separate manifold block which must be heated and insulated. So, this again reduces the construction and then the cost associated with preparing from the surrounding mold with an airspace. Now, plastic around the perimeter of the flow channel will freezes, so which is going to act as an insulating layer against the colder mold, which because it comes in contact with the colder mold, it also solidifies, and this provides a thermal insulating boundary of plastic. In the external heated system, it has the ability to provide the lowest pressure drop. So, that is why we go for externally heated. Whenever the pressure drop is less, then it definitely reduces the cost of the machine as well as the size of the machine compared to other systems. The flow channels are cylindrical in cross section and generally have a larger diameter than a cold runner system. Now, why this is an advantage means the cylindrical flow channel is the most efficient shape for melt flow to take place. Next, we will move on to gate. What is a gate? A gate is an entrance through which molten plastic enters the cavity. So, this is a cross-sectional view of a typical mold where starting from this sprue, this is actually the nozzle from either from injection molding machine or from the extrusion molding machine. The resin from this nozzle will actually enter this through the sprue followed by this runner. At the end of the runner is what we have the gate. So, therefore, this gate is an actual entry. This is the first time where the molten plastic has to cross and then it would start filling the cavity. These are the mold cavities. Now, the sprue, this region, and then this the runner and then the gate. This is a diagram showing once the product is formed, now the product will be ejected out with the help of this ejector pin. While ejecting, we do not eject the part alone, rather we would eject along with this sprue, runner and gate. So, therefore, the sprue, runner and gate will be discarded. This again a waste. This is a secondary operation or a post processing operation wherein these are removed and thrown out as a waste, but then the design of this sprue, runner and gate is going to have a direct effect on the cost as well as the quality on the formed product. Now, looking into the functions of the gate, the main function is it has to restrict, because it comes from a wide region and then it has to pass through a very narrow region and then it should enter the mold cavity. Therefore, it will restrict the flow, the direction of the molten plastic. Then it has to simplify cutting of a runner and moldings to simplify the finishing parts. As we have seen in the last slide, the screw, runner and gate are trimmed out. So, therefore, that finishing operations should not pose a challenge, and then it also has to cool quickly and it should solidify. If that is not the case, then backflow of the molten plastic will take place. The molten plastic which is getting filled up in the cavity, if it starts flowing in the reverse direction, that is possible when the gate does not solidify. Therefore, it has to quickly cool and solidify to avoid this backflow. Now, if you look into the types or the ways of classification of gates, one way is to categorize it into two types. One is restrictive gate. In the restrictive gate, it will actually reduce the dimensions of the entrance, that is the width or diameter. This will be restricted. In the non-restrictive gate, there is no such restriction in the entrance or with respect to the dimensions of the passage for the molten resin to fill the cavity. Now, a restrictive gate has a narrow entrance to the cavity to restrict the amount of molten plastic in order to improve filling in the cavity. Why we go for such a restrictive gate means this will improve the way in which the resin fills the cavity. The polymeric resin, as it is melted, and then it is very highly sensitive to temperature, in the sense its viscosity depends mainly on the temperature. Therefore, it has to fill at the same temperature, the same viscosity, the entire volume of the mold cavity. So, otherwise the product that is formed will not be uniform. Now, if you look into the features of the restrictive gate, it generally generates shear heat by going through a narrow gate. Because it is restricted to flow through a very narrow passage, it automatically heat is generated because of the plastic polymeric melt shearing on the surface of the mold, raising the temperature of the molten plastic. So, this again increases the temperature of the molten plastic and thereby improving the filling in the cavity, and also it reduces any residual stress that is being formed in the melt. Once you improve the temperature, then the residual stress would go away. The residual stress are formed in the melt because of the polymeric entanglements. Once there is a sudden drop in temperature, these polymeric chains will try to coil again. Now, if you increase the temperature, it will uncoil. In the process, it will release all the residual stress that is being stored, and hence what happens with respect to the reduction in the residual stress means this will reduce the part defect such as warp. So, warp is nothing but the reduction in the mechanical properties of the final product, and also as the cooling solidification time is shortened, molding cycle is also shortened. The cycle time is less. As the gate trace is less, it is possible to complete finishing process in a short time. So, there will not be any trace of gate that is left in the final product formed. Now, if you look into the examples or different types of gates for a restrictive gate, so these are the major types: a side gate in which the resin would enter through a side, and then the submarine gate. This again it acts like a submarine which goes down. A submarine goes down and then it can also come up above the sea. In the same way, this the functioning of the submarine gate is similar to that. And then pinpoint gate, where the resin enters through a point, through a very sharp point, and then a fan gate. Generally for optical products we go for this fan gate, and the film gate whenever you want to prepare a flat product, then we go for the film gate, and then the valve gate. We will see one by one. So, this is a three-dimensional diagram representing all these gates, the pin gate, flash gate, the fan gate. These are examples for a restrictive gate, and then these diaphragm gate and a tab gate, sprue gate are all examples for a non-restrictive gate. First, the side gate, it is also called as the edge gate. This gate is normally used for multi-impression molds, that is multi-cavity molds. We generally go for these side gates where the components are relatively small and of a flat or shallow nature. The size of the gate is again going to depend on the shape and thickness of the molding. For thick sections, the gate thickness should be approximately 75% of the component thickness. So, this is the gate thickness, this dimension W. This should be approximately 75% of the component thickness, and also it should be as wide as the width of the runner. So, here again not only in the side or edge gate, so the dimensions of the gate is important. So, the designing and optimizing the correct thickness and the length of the gate is an important feature in mold design. Next, we will move on to submarine gate. This gate will be automatically cut off during the mold opening. So, therefore, one need not go for any secondary operation in removing this gate. As and when the mold is opened, the gate would also be cut off. And then with respect to the positioning of the gate, it is more flexible. That is, there is no restriction to have it in any one place. One can have, if the design allows you to have it in the front side, you can have, or in the side or in the back. That is, on the any part of the product that is being formed, one can position a submarine gate. The gate needs to be thought about not to be left inside the cavity. One need not worry about whether the gate has to be left inside the cavity or not. So, this is a typical submarine gate. This is the sprue followed by a runner. From the runner, this is actually the submarine gate or the tunnel gate. Now, once the product is ejected, this part would go up. In the process, this gate would also move up, and as a result, it would be cut off from the mold. Next, the restricted gate or pin gate. So, this is a typical diagram of pin gate, where the entry of the molten plastic is through a very narrow region. That is why it is called a pin. This type of gating is again used for multi-cavity mold. Now, finishing operations can often be eliminated because the gate itself will be of small size, and this will automatically broken off during the ejection of the molding. The gate must not be too small, otherwise the filling of the cavity is impaired. Even though the dimensions of pin gate is very small, at the same time one has to optimize it in such a way the cavity, this is the cavity. The cavity is also has been filled at a optimum rate. Also, under the effect of high injection pressures, frictional heating would also develop with respect to the material pass through the gate. This could lead to splash marking and burning on the finished component. So, these are some of the drawbacks. Now, when the plastic mold is injected at a very high pressure through this, this could also result in some splash mark that is being formed on the surface. It appears as though the product is burnt. Next, we will move on to fan gate. Where we go for fan gate means for thick section molding such as optical lenses. So, nowadays people go for optical lenses instead of wearing spectacles. Those are prepared by using a fan gate. This is because it enables the runner to be made of an adequate size to help prevent the material from chilling off. Once the gate size is going to be more thicker, then what happens is when the melt starts flowing through that, and then the region behind that will slowly try to solidify. So, therefore, adequate size has to be provided. But this happens particularly when it is injected very slowly. Now, you inject very slowly, then that will help it to forming to solidify. It also allows sufficient follow pressure into the cavity during the cooling contraction. Once it is solidified, the correct pressure has to be maintained for the product to be formed. So, this is a typical example for a fan gate usually used to prepare optical products. Next, the film gate, it is also called as a flash gate. So, this is a typical diagram showing the flash gate. The polymeric resin will enter through this direction. This gate type can be used successfully for long flat components of course, a thin section. It enables a large cavity to be filled quickly and also consistently, because there is a very wide region here. A large cavity could be filled in a short time. Of course, the thickness should be less. The length and width of the article and the flow pattern required will dictate the actual this length of this. This is the length of this gate. This again depends on this length and width of the product that is being prepared. Next, we will move on to non-restrictive gate. A non-restrictive gate involves a method in which the molten plastic fills up in the cavity directly from the sprue. So, there is no gate at all here. Instead, the resin from the sprue will straight away fill the cavity. Direct gate is a typical example for the non-restrictive gate. The next to the direct gate is also called sprue gate. So, this is a typical diagram showing sprue gate. This is the sprue, that is why it is called a sprue gate. This type of gate is the preferred gate and is normally used for a single impression molds. So, that is at a one time one product alone would be formed, and also it is especially suitable when the component is cup shaped, and also it involves a base. Typical plastic cups what we use for drinking water is prepared using a sprue gate. Compared to a side gate, the material flow is more direct, and therefore it will experience minimum pressure loss, and also it will also reduce the shearing rate that is required. However, this can result in a high stress concentration. The high stress concentration occurs at the surface of this product, and this is caused by the polymer at the gate area, as well as problems with the material freeze off, which can lead to sinking. So, sinking is nothing but the polymer solidifying prematurely before it is converted into the product. This sinking particularly takes place around this gate. There is also need to remove the gate once the part is finished. Therefore, it requires secondary operations or post processing operations. Next, we will move on to tap gate. This is a tap gate. This type of gating can be used as an alternative to side gating, because here also the resin enters through a side. Instead of entering on the sideways directly to the product, a elbow shaped provision is given, which is what we call it as a tab. That the resin flows through this tab, and then it starts filling the mold cavity. This is the product that is going to be formed, and the mold cavity. And then this tap gate is suitable for multi impression molds, and also it is suitable to produce articles of a flat or a shallow nature. So, that means one cannot go for a particle or a product where it involves more depth. Now, if you look into the advantages over the normal side gates, here the design minimizes the jetting of the material. So, jetting of the material is nothing but the resin trying to forcefully enter through the mold cavity. So, that can be reduced because it is passed through a tab and then only it enters the cavity. So, therefore, this will minimize this jetting effect. What happens with respect to jetting means formation of weld lines and flow marks. So, these are the surface irregularities that is being formed on the product. This will actually reduce it aesthetic look, as well as this will also have a great effect with respect to the mechanical properties, and then these flow marks will actually result in reduction in the dimension, particularly when you use that component to be fitted into another place where the provision will be given exactly as per the dimensions. Now, it also creates turbulence because it takes a elbow shaped flow. It creates a turbulence, which in fact will help in dispersing, particularly when you go for a dry colored material. The dispersion, one can also add the colorant in the runner itself, thereby complete dispersion of this colorant with respect to resin would take place. Next, the diaphragm gate, which is also called as a disc gate. This is a typical example for a diaphragm gate. So, in the diaphragm gate, what happens is a hollow space is available, a circular hollow space is available inside the cavity. A diaphragm gate is often used for gating cylindrical or round parts that have an open inside diameter. So, this inside portion is open. The typical gate thickness is about 0.25 to 1.27 mm. It is used when concentricity is an important dimensional requirement, that is the symmetry of the product is more stringent, then a diaphragm gate is used, and the presence of a weld line is objectionable. So, this because of this arrangement, there is less possibility for the weld line to be formed on the surface of the product. This gate is again essentially a flash gate around the inside edge of the part rather than on the surface of the product. Here this diaphragm gate is a flash gate around the inside edge of the part. So, this is the inside edge. Since the diaphragm is fed from a concentric sprue, this is the concentric sprue or a stub runner drop, uniform flow to all parts of the gate is easy to maintain. So, therefore, one can ensure that the cavity is filled, the entire region of the cavity is filled at the appropriate or more uniform rate. Next we will move on to ring gate. So, like a diaphragm gate, a ring gate is also used to prepare a cylindrical or round part, but then it is not always recommended except for some specific applications. Now, what happens with a ring gate is the material flows freely around the core before it moves down as a uniform tube like extrusion to fill the mold. So, that is why it is a ring. It first flows like a uniform tube like extrusion before it starts filling the mold. The typical gate thickness is again 0.25 to 1.6 mm. Now, the next way to classify gates is whether it is trimmed automatically or manually, because once the product is ejected out, the sprue, runner and gates are all trimmed out. Now, the automatically trimmed gates incorporate features in the tool to break the gate or shear the gate. So, shearing takes place, thereby removing the gate as the molding tool is opened to eject the part. Normally, automatically trimmed gates are used to avoid gate removal as a secondary operation, particularly in automatic molding machines where the product has to be formed instantaneously without any post operation like a secondary operation, and also to maintain a consistent cycle time for all shots. So, the normal problem with the manually trimmed gates is the cycle time would vary for each and every shot. So, that is going to have an effect on the product that is being formed. The cycle time is the actual time which starts from the resin that is being injected through the nozzle, the time it takes to flow through the runner, and then the time it takes to fill the mold cavity, and then the time it takes to cool or solidify, and the final product is formed. So, therefore, if this cycle time is going to change for each and every injection shot, then that will not result in a product with uniform properties, and also this will also minimize the gate scars. Gate scars are nothing but the traces of the gate that is being carried over the product even once the gate is also removed. Now, the pin gate is a typical example for automatically trimmed gates. Next, the manually trimmed gates. The manually trimmed gates are those that require an operator to separate parts. This has to be done manually from runners during a secondary operation. This sprue gate, tab gate, edge gate, fan gate, disc gate and flash gate are all comes under these manually trimmed gates. Now, despite the number of advantages with automatically trimmed gates, the reasons why we go for a manually trimmed gates are: the gate is too bulky to be sheared from the part as the tool is opened. Once the mold is opened and the product is ejected, the gate is too bulky. This usually happens particularly when you prepare a product of more thickness or more depth, then one has to increase the dimensions of the gate. So, therefore, this will be particularly bulky, therefore, this could normally could not be sheared. And also some shear sensitive materials, particularly PVC. PVC is more sensitive to shear, should not be exposed to high shear rates. Therefore, this is inherent to the design of automatically trimmed gates. So, automatically trimmed gates are designed in such a way it is normally subjected to a very high shear rate. Now, simultaneous flow distribution across a wide front to achieve specific orientation of fibers of molecules often precludes automatic gate trimming. Nowadays, even with thermoplastics, we go for some reinforcements in the form of this fiber only to ensure that the flow distribution is uniform. So, therefore, in all these cases, we go for manually trimmed gates. Next important thing with respect to the gate is the for determining the correct position of the gate, that is where to provide the gate with respect to the product or the part. Now, these are the points to be considered. Now, you set a gate position where the molten plastic finished filling up in each cavity simultaneously, same as multiple point gates. Now, set a gate position to an unremarkable area of your part or where finishing process can be easily done. So, this could be done easily like this. So, therefore, here these are the gate positions. You could see all these cavity would be filling up at this simultaneously without any lacking, and also the removal is also easy. And the other thing is other points is to set a gate position to the thickest area of your part. Wherever the part where the thickness of the part is more, there one can provide the gate. This will avoid the sink formation due to mold shrinkage, and also the filling up of the molten plastic using the wall surface in order to not to generate jetting. So, that could be done like this. So, this is a typical case where the thickest part of the product is the location where the gate is provided, and also avoid injecting from the place where the formation of air or gas that is being generated from the molten plastic. So, therefore, one should avoid providing gate here. Therefore, so these are the things to be considered. So, to summarize, today we have discussed about the final part of the feed system, which is more about the hot runner system and the gates. In the gates, we have discussed about the restrictive gate and the non-restrictive gates, and then the design features of a gate, and then the position of the gate. So, determining the correct position of the gate. So, that will complete the feed system. So, after looking into this episode, these are the questions the viewers should try to answer. What is a defined gate? List down the functions of the gate. State the typical characteristic features of a restrictive gate and then a non-restrictive gate. State the reasons for using manually trimmed gates. Why we go for using these manually trimmed gates. What are the points to be considered in determining the position of the gate? Thank you.